Welcome to my concept of Thevenin and Norton Equivalent circuits using myDAQ and LabView. The objective of this laboratory is to experimentally determine the Thevenin equivalent circuit of a resistive network driven by a DC voltage source, as well as the parallel current and resistance for the corresponding Norton equivalent circuit. What are they? A Thevenin equivalent circuit is an independent voltage source, represented by VTH, in series with a resistor, RTH. It is a simplified circuit that is the equivalent of an original circuit made up of only voltage, current sources, and resistors when observed from the terminals A and B. A Norton equivalent circuit is an independent current source in parallel with the Norton equivalent resistance. It is derived from the Thevenin equivalent circuit by performing a source transformation. Why are they useful? The Thevenin and Norton equivalents are used to simplify circuits in order to observe terminal behavior. It allows engineers to model a circuit at a higher level instead of having to worry about all of the inner workings. Who derived the Thevenin theorem? It was first derived by Hermann von Helmholtz in 1853. Later, a man named Leon Charles Thevenin independently derived the same result in 1883. Now, we're going to go over the pre-lab procedure. First, we need to create a VI in LabView to generate a 3-volt voltage source using the myDAQ and DAQ assistant tools. Within LabView, we have created a new VI. Here, we are going to use the myDAQ and the DAQ assistant tool to generate a 3-volt voltage source. To do this, go to your block diagram, right-click, go to Input, and select the DAQ assistant. Place this on your block diagram. Next, we're going to click Generate Signals, Analog Output, and we're going to select Voltage. Here, we select the output channel for our voltage source. Select AO0. Next, we're going to change the generation mode from N samples to 1 sample on demand. Click OK. After you have set up your DAQ assistant, we need to assign a numeric control in order to set the amount of voltage that we want our myDAQ to generate. So we're going to go right-click on Data, click Create, and go to Control. On the left-hand side, our numeric control has appeared. We can set that to 3. Next, we must design the circuit in the figure below using the 3-volt voltage source that we created using the myDAQ. We're going to use the myDAQ digital multimeter to read the voltage and current across every resistor and record them in LabView. To open the LabView digital multimeter, you have to first start the NI-Elvis instrument launcher. Next, select DMM. Here, the digital multimeter has launched, and we can select various different settings from DC voltage to DC current to resistance. I select the mode and switch to auto to automatically calibrate the multimeter to read whatever it is that I want to read. With the digital multimeter loaded, you can now use the two probes that come with the myDAQ to measure the voltage across each resistor. Place the positive probe on one end of the resistor and the negative probe on the other. Wait for the measurement to load in the digital multimeter and record it in LabView. To measure the current across each resistor, you will need to change the red probe on the myDAQ from this end to this end. Once that has been changed, you can now change your multimeter to DC current. It is important that when measuring the current across a resistor to get an accurate reading, that you create a small short circuit in order to read the measurement. So what I'm doing is I am deactivating the 1 kilo ohm resistor, resistor 2, and now I am placing my multimeter probes across the voltage source and resistor 1. And I get a reading of 0.64 milliamps. Repeat this process for all of the resistors in the circuit. You can check your recordings against Multisim by doing the following. Click Simulate, go to Analysis, and select DC operating point. Here, move over all of the currents for each resistor to the right-hand side. I have already done this. I'm going to remove the voltages that I'd added on earlier. Click Simulate. Here, we can see all of the simulated currents for each resistor. This will make sure that your readings that you're getting from myDAQ are at least in the same ballpark as this virtual circuit. The next part of the pre-lab, we will be using LabView to verify that the power generated by the source is equivalent to the power dissipated by the resistors. To do this, we must construct a VI. An example VI is shown. Next, we will be using the myDAQ digital multimeter to measure the open circuit voltage and the short circuit current as shown below. To measure the open circuit voltage and the short circuit current, we have to remove the 5.6 kilo ohm resistor from the circuit. Now we will be measuring the short circuit current. I will place the red node at the end of the 100 kilo ohm resistor and the negative probe to the ground. We'll get our recording. Next, we'll have to switch again the probe back to the other side. Repeat the process, but this time setting the digital multimeter to voltage and record the measurement. The next step in the pre-lab is to calculate the R Thevenin as well as the max power that can be transferred across the load. To do this, we construct a VI. An example is shown. Now we are moving on to the main part of the lab. The objective of this laboratory is to experimentally determine the Thevenin equivalent circuit of a resistive network driven by a DC voltage source, as well as the parallel current and resistance for the corresponding Norton equivalent circuit. The maximum power transfer theorem will also be verified empirically using LabView. First, we need to design a circuit that looks like the one shown in the figure that will have a Thevenin resistance of 3.9 kilo ohms. Be sure not to use any resistors that you use in your pre-lab, except that of the load resistor. You can design the circuit any way you want, as long as it has a Thevenin resistance of 3.9 kilo ohms. The circuit that I designed is shown. Using the digital multimeter, measure the experimental values of all resistances in the circuit shown before they are placed into the circuit. Measure and record in LabView the voltage across every element and the current flowing through every element. Similar to the pre-lab, we also need to measure and record the voltage across every element and the current flowing through every element. To do this, simply place the nodes across the resistor, each resistor, to get the voltage flowing through them. To get the current, we need to change the red node on the multimeter to the other slot. Then we can measure the currents across each resistor. Parameters for the Thevenin and Norton equivalents will be measured for the circuit to the left of the load resistance, RL. Since we need the open circuit voltage and the short circuit current to calculate all relevant parameters, be sure to measure these quantities as shown. Record them in LabView. We need to measure the open circuit voltage and the short circuit current on our newly designed circuit. In order to do this, we do this very similarly to the pre-lab, where we remove the load resistor, and then we take our nodes and we place them across resistor 4 to the ground. We take both measurements for voltage and current, and that will give us our open circuit voltage and our short circuit current. We are also able to calculate the Thevenin and Norton resistance directly by turning off all independent sources and measuring the equivalent resistance of the network. Measure the Thevenin resistance to the left of the terminals. We can also calculate the Thevenin and Norton resistance directly by turning off all independent sources and measuring the equivalent resistance of the network. In order to do this, we deactivate our 3-volt voltage source. Next, we need to remove the load resistor, and then we need to create the part of the circuit where the voltage source was in order to complete the circuit. We then bring up our digital multimeter on our computer, set it to ohms, run it continuously, and now if we place our nodes across resistor 4, we will get our Thevenin resistance, which is 3.9 kilo ohms. We will now empirically verify the maximum power transfer theorem by measuring the power dissipated by the load over a range of resistance values. Choose 10 resistors for RL from 0 to 5.6 kilo ohms in the complete circuit, measuring the power dissipated by the load for each resistor value, and record the values in LabView. What value of RL provides maximum power transfer to the load? Does this agree with your theoretical expectations? After we have captured all of the necessary data from our circuit that we have designed, we can then build this VI. In this VI on the front panel, on the top left, we have the measured and theoretical values. From that, we can calculate the power of all of the elements, and we can calculate the P max, the max power that we can theoretically get. Below that, we have our experimental values, where we chose 10 different resistors to test and validate the maximum power transfer theorem. We then place these resistors in our circuit and calculate the voltages across these resistors. From that, we can calculate the current and the power being distributed to the load. We then built a graph and we calculated the percent error.